This is the last video of the curve sketching example problem series of videos. And what I want to do here in this last problem is make sure that I make it clear what the difference is between endpoints and critical points. Before the start of these example problems, I made a video dedicated to this topic. But I'm not sure as I went through each of the previous 14 example problems that I made this point clear. So, and I think this is a good example to talk about it. So, all right, step one is you write the domain. All right, so this is a rational function. We can factor the denominator. It's the difference of two squares. We can also factor the numerator. Okay, and what we also can do is we could take out a -1 to make this x minus 5. So let's do that. So okay, and then this we could make x plus 5. 5 plus x is the same thing as x plus 5. Okay, so now we can see we can cross these out, and we are left with okay, so this simplifies to this. However, if we think about what the domain is, so the domain, just looking at this, the domain seems like it's just x is equal to 5. You can't divide by 0, x is equal to 5. But the domain is going to be that you can't, it's all real numbers except not including 5 and -5. Because why? Yeah, it simplifies to this. But if you come back to the original function, if you plug in 5 or -5, you're going to be dividing by 0. And so, okay, but what does this mean? The idea is we're going to draw this curve, y is equal to minus x over x minus 5. And when you draw that curve, this curve is going to exist for all real numbers except x is equal to 5. But then we're going to go on that curve. We're going to go to x is equal to -5 and put a hole at x is equal to -5. That's the idea. This curve is this exact curve except with a hole at x is equal to -5. Okay, so the domain then is all real numbers except not including -5 and 5. That's the domain. And we'll come back to the range later. Okay, now the idea is, so what we're going to do is we're going to, after we look at intercepts and symmetry, we're then going to analyze the endpoint behavior. And what I mentioned in that video before these example problems is, so what's the difference between an endpoint and a critical point? Because when we're analyzing the endpoint behavior, what that means is we're going to take the limit as x approaches the endpoints. And typically the endpoints are just going to be you go to the leftmost side of the domain and to the rightmost side of the domain. And that's the only endpoints. But there are situations where, so there was a previous example problem, there was a domain that was -∞ to -1, and then 1 to infinity. In this case, the endpoints are -∞, infinity, as well as -1 and 1. So you take the limit as x, to analyze the endpoint behavior, you take the limit as x approaches -∞ of the function, the limit as x approaches infinity of the function, the limit as x approaches -1 from the right, and the limit as x approaches 1 from the left. Okay, so these must be endpoints then. Why isn't -5 and 5 endpoints? These aren't, we don't consider these endpoints because it's just one single number where the function doesn't exist. So you've got this, the function exists for all numbers are right around minus 5 and 5. It's just that one single number where the function doesn't exist. That's not, we don't consider that an endpoint. We consider that's not considered an endpoint. This is going to show up. These are points of interest, but these are going to show up as critical numbers. However, with this minus 1 and 1, they're not, minus 1 is not alone, right? If you go to minus 1.1, minus 1.2, minus 2, if you go to minus 0.5, 0, 0.5, those numbers don't exist either. So these numbers they're not alone. They're right. And that's the idea why they're considered endpoints. If you've got a gap in the domain where the function doesn't exist and it's two or more numbers grouped together, then you consider that an endpoint. And the main reason is because if you're going to consider minus 1 a critical point, then you might as well consider 0 a critical point and 0.5 a critical point and minus 0.5 a critical point. That doesn't make sense. Whereas in this situation, it works. It's more in conjunction with what they teach in the calculus textbook, in that since it's this one single number alone by itself, then this is going to show up because wherever the function doesn't exist, then the first or second derivative don't exist. So this is going to show up as a critical point. And that's how we want to analyze it. That's more in conjunction with the way the calculus book teaches it, having a number like this show up as a critical point. Okay. So, all right. So with that in mind, we've only got two endpoints here, though, minus infinity and infinity. All right. Now let's analyze for the asymptotes. So let's set x equal to 0 and solve for y. So this is 0 over 25. Okay, so the origin is an intercept. All right, now let's set y equal to 0 and solve for x to get the x-intercepts. And so this x squared plus 5x is equal to 0. That's what we're solving for. So x plus 5. So x is equal to 0 and x is equal to minus 5. All right. So 1, 2, 3, 4, 5. There we go. Well, actually, no, because we're plotting. Let's plot so we don't. I don't want to confuse myself here. We're going to plot this curve. So x, if you set this equal to 0, there is no intercept at x equal to minus 5. So really, we would say we would put minus 5 here, and so we're going to plot this, but then just make sure we put a hole at x is equal to minus 5. Okay, so then minus x over x minus 5 is equal to 0. X is equal to 0. Okay, that might be confusing. The reason is because, so that makes minus 5 makes the numerator 0. Okay, but it also makes the denominator 0. You see? So what I did was I set this equal to 0. And I solved for when the numerator equals 0. Usually that's no problem because in any other scenario, if it's not the same term in the numerator and denominator, then whatever makes the numerator 0 is going to make the whole function 0. Because the numerator becomes 0 and the denominator is something non-zero. But you can't, if you have a situation where you have the same factor in the numerator and denominator, then you can't say that, well, if that factor in the numerator becomes 0, then that makes the function 0. It's not true. Okay? All right. Now, symmetry, is this an even function? So y of minus x is, okay, so this is minus x over x plus 5. And this is not equal to the original function. Okay, what about, is this an odd function? So this would be x over x plus 5. And this is not equal to y of minus x, as we can see. Okay, and then this is not going to be periodic either. We know rational functions aren't periodic. Okay. All right, the endpoint behavior. We've only got 2 endpoints here. These aren't endpoints. So, but if we had, we could potentially have endpoints in the middle that aren't to the full left and the full right. But in this case, we don't. But if we had those, we would include those in the endpoint analysis. So as x approaches minus infinity of y is equal to, okay, so minus x over x minus 5. Well, let me actually do the real function here. Okay. Okay, so store as e. All right. So now we want to take the limit as x approaches negative infinity of e. Okay, this is minus 1. Now the limit as x approaches positive infinity is also equal to minus 1. Okay, so x is equal to minus 1 is a horizontal asymptote, or y is equal to minus 1. All right. Next, the critical points. So actually, let's come to a new, let's get a clean sheet here. Okay, so the critical points, we take the derivative with respect to x, the equation, okay? Now, there's no points where this equals 0, but it says that x is equal to 5 is a point where the first derivative doesn't exist. Okay, so all right, so the first derivative, we have x is equal to 5, and so is that it? That's the only critical point? This is a little confusing because, no, another critical point is x is equal to minus 5. Why is that? Because by definition, if a point in a function doesn't exist, so like okay, the derivative, in order for a derivative to exist at a point, the function has to exist at that point. That's a definition. So since we know the function doesn't exist at x is equal to 5 or minus 5, then we know the derivative won't exist there either. And the only reason it doesn't show up in the actual derivative formula is because of the way it simplifies to this. But we know, though, that this is minus 5 is a critical point as well, and it's going to be the same with the second derivative. We know for sure x is equal to minus 5 is going to be a critical point with respect to the second derivative. Let's check. So, and so is x is equal to 5. Okay. All right. So now the process is, the way you do this for curve sketching or just for analyzing functions is when it comes to critical points with respect to the first or second derivative, if you have a critical point where the first derivative is equal to 0 or the second derivative is equal to 0, then you have a lot of information about that point. You know the slope is going to be 0 or the concavity is going to be 0. Also, and then you also know that the function is continuous there because the derivative exists there. However, when it comes to critical points where the first derivative or the second derivative doesn't exist, there's a lot more ambiguity about what's going on at that point. Because why? Because the first derivative could not exist at a point, and the function could be continuous like that. But here the slope isn't vertical. It could be continuous and the slope could be vertical. or it could be a vertical asymptote, or it could be a discontinuity, any kind of discontinuity. And it's a similar kind of idea with the second derivative. So that's why when you have a critical point that's associated with the first or second derivative not existing, then you need to analyze that point further. But you don't really have to do this with whenever if the first derivative is equal to 0 or the second derivative is equal to 0. So what we want to do is let's take how do you analyze it? Well, you take the limit as x approaches that point from the left and the right of the function, then do the same thing for the first derivative and the same thing for the second derivative. That's how you're going to analyze it the best. You're going to take the limit as x approaches that value from the left and the right of the function first and second derivative. And you could omit some of those if you feel like you've analyzed the limit of as x approaches that value of the function and maybe just the first derivative, and you feel like you have enough information, you can stop there if you want. But in general, to do a full analysis, you take the limit as x approaches that each of those points from the left and the right using the first, second, the function, the first derivative, and the second derivative. So, okay, let's take the limit as x approaches 5 from the left of the function and the limit as x approaches 5 from the right of the function, okay? So we should be able to use as x approaches 5, this should work here. Okay, yeah, there we go, minus infinity. And then infinity. So there you go. This tells us that the point x is equal to 5 is a vertical asymptote. But sometimes in other situations, this might approach an actual number. So what does that mean? Well, okay, if let's say this limit approached the number 3 from the left and the right, well, then you know you're going to have one of these situations. Something like that, or maybe something like that, like a vertical slope. It's going to be continuous there is what that's saying. It's continuous there. And so in a situation like that, then you take the limit as x approaches that point from the left and the right of the derivative, and it'll give you a sense. If that derivative goes to infinity, then you know it's a vertical slope. We saw examples of vertical slopes like this. I think those look like x to the 1/3. So approaching the derivative approaching from the left was negative infinity, and then from the right was positive infinity. And so you see what here it would be both positive as the limit as x approaches this point from the left and the right would be positive infinity. Here it wouldn't the derivative wouldn't be infinity. The limit as x approaches this from the left and right wouldn't be infinity. So you know it wouldn't be a vertical slope. But if you got the limit as x approaches 5 from the left to be like the number 3 and from the right the number -1, then you know you've got like a jump discontinuity, right? You got something like this. And so that's how, if you take the limit as x approaches the value where the first or second derivative doesn't exist from the left and the right of the function of the first derivative and of the second derivative, that'll tell you everything you need to know about that point. Okay, so let's do now the limit as x approaches -5 from the left or from the right and from the left. Okay, so -5 minus 1/2 minus 1/2. See, that's not a vertical asymptote. And this makes sense because we know this is going to be a removable discontinuity. We know that. It's just going to be a hole in the graph. So we're going to have the graph is going to be, when we get to x equal to -5, it's going to do, okay, 1, 2, 3, 4, 1, 2, 3, 4, 5. It's going to do this. And so that's why the limit as x approaches minus 5 from the left and the right is the same, but it's still a critical point because the function doesn't exist here. So neither does the first or second derivative. So it's not a vertical asymptote. Okay, and so let's do limit as x approaches 5 from the right of the first derivative, the limit as x approaches 5 from the left of the first derivative, and then the limit as x approaches minus 5 from the right, and the limit as x approaches minus 5 from the left, all of the first derivative. Okay, so what we'll do is get the first derivative and store that as d. Okay, there's the first derivative. Then take the limit, and you don't have to do all this analysis every time. I'm just trying to illustrate this for you. The limit as x approaches 5 from the positive direction of d is infinity. The limit as x approaches 5 from the, okay, is infinity. And then minus 5 is 1 over 20. And then this should also be 1 over 20 when you do it from the, yeah. Okay, so let me put a line here. All right, and then you could do the same idea if you need with the second derivative. Limit as x approaches minus 5 okay, so this what we would do is take the second derivative, store that as, we'll say, c for curvature, then take the limit as x approaches 5 from the positive direction of c, this is negative infinity, then do 5 from the left, infinity, then do minus 5 from the right, 1 over 100, and this should be exactly the same coming from the left, 1 over 100. Okay. Again, you don't necessarily have to do this, all of this, for every single time you have a critical point that where the function doesn't exist. But I'm doing this for illustration. You have the option to do as much as you need. Okay, so like for example, at as x approaches 5 of the function, once we see we have vertical asymptotes, we probably didn't need to do x approaching 5 of the first derivative because we know it's a vertical asymptote. So in other words, we know that. So let's draw x approaching 5. 1, 2, 3, 4, 5. So okay, so as x approaches 5 from the positive direction, we're going to negative infinity, and then from the negative direction, it's going to positive infinity. You don't really, I mean, that's all you. This is all you're going to draw, you know. But yeah, so the derivative as you go to infinity, the derivative is also going to infinity. That makes sense, right? And then the curvature is going to negative infinity, and the coming in this direction, positive infinity in this direction. So just interesting to look at what the derivative and the curvature are doing as you come close to the vertical asymptote. But you know, you don't really need to do that. You probably didn't need to. It would be unnecessary to take these derivatives of these limits of the first and second derivative approaching the asymptote. Okay. Okay, so but with these limits, now we know we can figure out what exactly is going on at these critical points where the first or second derivative doesn't exist. Okay, so with that, we know what's going on at the endpoints. We know what's happening as x approaches plus or minus infinity. But for the domain where there was endpoints between -1 and 1, those were endpoints. Those endpoints might be vertical asymptotes. So the function, let's say the function didn't exist between -1 and 1. Well, these endpoints might be vertical asymptotes. They might not be. That's why when you analyze the endpoint behavior, you can see what's going on at those endpoints. Okay, so this is how you can get a sense for what's going on at all points on the graph. Okay, now before we sketch the graph, we need to do the intervals of increasing and decreasing intervals and the intervals of concavity. And there's something else I need to point out here. So what we do is we draw a line. This is the process. We draw a line, and we will put the critical, typically the majority of the time, we're just putting all the critical points with respect to the first derivative when it comes to the increasing, decreasing intervals, okay? However, that you are going to do that, but you're also going to include any endpoints that are that are away from the full far left and the far right if you have those. So in this situation, for this domain, no, it was minus infinity to -1. In this situation, we would include for the intervals of increasing and decreasing, we'd put all the critical points, and we'd also include this -1 and 1, because the first derivative could potentially change signs going from -1 to 1. And same exact idea with the second derivative. Now the farmost endpoints, we don't include those because the function can't switch across those, because you can't, if you're only defined on a domain like, that's the full domain. You can't switch. There is no function over here. There's no switching here. There's no function to the left of this. But there is if the domain, if you have a function that does this, okay, well, these are endpoints, but these are also endpoints, but we can switch first or second derivative sign here, okay? So you need to include those endpoints that are away from the far left and the far right if you have those. In this situation, we don't have any of those. So all we're going to include are just the critical points, okay? Well, let me do this. Okay. All right. Okay, so, all right. Derivative, well, no, we already took that. So evaluate D, where is it? D with x is equal to, and let's put -6. It's positive, so increasing. All right. What about D with x is equal to 0? 0.2, so increasing. And then D with x is equal to anything above 5. Increasing, so increasing everywhere. Okay. Now, the second derivative, so 0 minus 5, 5. Okay, so this, I called this function C with x is equal to -6. So concave up with x is equal to 0, concave up, and then with x is equal to 6, concave down. Okay. All right. Now, so then the next step, what we do is we look and see, do we have any local maxes or mins or inflection points? All right. And the rule here is if you're dealing with an endpoint, okay, so if you're an endpoint that's away from the far left and the far right. So again, that -1 to 1, those are endpoints away from the far left and the far right. that can't be a local max or min or an inflection point. No, even if it changes signs going across that point, that can't be a local max or min or inflection point. Okay, that's the first thing to note. And then just the second thing to note, I've mentioned this multiple times, but you can potentially have a local max or min at a discontinuity, at a point where the first derivative doesn't exist. We talked about this. Okay. So just to clarify, like the first derivative might not exist here, or it wouldn't exist at something like that. That could be a local max or min, but you could also have the first derivative not exist here, but this would be a local min. Okay, and then obviously if the first derivative exists, that, like, you know, if it's the slope is 0, that can be a local max or min. All right. Now, okay, so just note that. Now, when it comes to the inflection points, the function has to be continuous at the point to have an inflection point. So, like, yeah, you could be doing like this. Well, no, okay, it would be concave up, and then, you know, something like that, right? So the second derivative doesn't exist here, but the function's continuous and it changes from concave up to concave down. That's an inflection point. But if it's different from the first derivative from the local maxes and mins, if at a discontinuity in the function, you can't have an inflection point. Okay. And so, okay, if we look at that, well, there's no local maxes or mins, nothing changes signs here. We switch from concave up to concave down here at x is equal to 5. Okay, could this be an inflection point? Well, no, because the function doesn't exist here. The function has to exist at the point to have an inflection point. You can't have an inflection point at a vertical asymptote. Okay, so all right. Now we can draw the function. So, all right, as x approaches 5 from the left, the function goes to negative infinity. As x approaches 5 from the right, no, as x approaches 5 from the left, the function goes to positive infinity. And then from the right, it goes to negative infinity. Okay? As x approaches minus, so when x is equal to minus 5, the function is equal to, it's not equal to minus 1/2, but that's where the hole is. So 1, 2, 3, 4, 5, and then minus 1/2. So there's going to be the hole. Okay, that's what this shows us. All right, and it makes sense that coming into this point here, the slopes, the slope's going to be the same coming from the left and from the right, and so is the concavity. It's just a hole. Okay, now the horizontal asymptotes, as x approaches infinity, the function approaches minus 1. Okay, so, and we know it's going to be below minus 1 because it's going to have to be in conjunction with this portion of the graph. As x approaches negative infinity, the function approaches minus 1, but it's going to be above minus 1. Okay, so all right, let's now connect the graphs. Oh, and then we're going to have this. We can't just do this. Why not? Because then we don't have an x-intercept here and a y-intercept here. So the only intercepts are here, right? Like that. And then here. Okay, so we have the intercepts correct. We have the horizontal asymptotes correct. We've got the vertical asymptote correct here. The hole, okay, let's see. It's increasing everywhere. Yep. Concave up when x is less than 5. Concave down when x is greater than 5. And so there you go. That's it. Now we can look at we fill out the range. Looking at this, what's the range going to be? It's all real numbers except for minus 1. Right? It could be anything, but there's no x that you can input. You could input any x that's within the domain, and you could get any number on the y except for minus 1.